Hi everybody, we're going to cover how to do t-tests and correlations in JASP in this video. So I'm going to start with an example of a single sample t-test, and this is really useful when you're concerned with comparing one group of people to some sort of known average. So let's say you have a standardized score that you compare people to and you're concerned if they're too low or too high. That would be Z. But if you have an entire group of people, and not just one, we can test whether that group of people is lower or higher than some, let's say, national average. And so this gifted honors program is claiming that their scores are significantly higher than the national average for the SAT. So if the national average is a 1250, is their score significantly better? So what we want to do is open that up in JASP. So this file is on Blackboard. I'm going to open that file. Okay, kitty cat. Get off the table. There you go. So this one is single sample T. So I have a list of the SAT scores from their current students. So to run this, what you do is you click Ttest, and then it's one sample t-test, which is the same thing as a single sample t-test. Take this score, move it over to the right, and it will actually auto-calculate this t-test. But look how big this number is, 47. A ratio of 47 to 1 is a little extreme, and that's because I have not come down here and entered mu, which is considered the test value. So this is a spot right here where you enter the number that you want to compare it to. So as soon as I type in that number and click outside that box, you will watch over here, this is going to change. And so this recalculated. So it compared that score to 1250 now, instead of comparing it to 0. Sometimes 0 might be the number you are interested in, but in this case we're comparing everything to 1250. Right? Another thing that we're going to want to do is add our descriptive statistics, so that we can see, so we have 15 people, a mean of 1370. So the scores from this group are higher than the national average, and significantly so because our p-value is less than 0.05. Remember, we're setting alpha, which is our criterion for a type 1 error, to 0.05, and we want our actual p-value to be less than that. So our actual p-value is 0.001. So remember to keep the distinction between alpha, which is the criterion we set, and found p, or p actual, if you will, as different things. We haven't really talked about what degrees of freedom are, and we'll get into this more when we do ANOVAs, but a quick introduction on degrees of freedom is that they're the number of scores that are free to vary. And that definition is not usually very clear to people. And so if I have 15 people, it's the number of scores that I can change and keep the same mean. And so I can change every score but one. Technically, degrees of freedom are the number of participants minus the number of scores that you have to calculate to get your test statistic, which in this case is the mean for the group. But that's also confusing to people, so I always think about this as how many scores can I change and keep the same statistics, so keep that same mean value, because that's what we're really interested in, is the mean as a point estimate. We can also ask it to add the confidence interval, which will give us the confidence interval of the mean here. And so that means that this is a range of scores that I should believe, right? Or it's a range of scores that I have confidence in. Most confidence intervals are plus and minus around 2 standard errors. So here's standard error here. And so that's about plus and minus 60. And so what really confidence intervals technically are the range of data that 95% of the time I would expect to find the true population mean. It's their technical definition. But that's a really difficult thing to swallow when you are testing this in null hypothesis testing, where we don't even really expect the null to be true. So I don't really expect there to be no difference between our test group and the national average. I do expect them to be somehow different. And so the way I think about confidence intervals is I think about them as a sort of a range of scores that one would expect from this sample given the error. So it's kind of a not sensitivity, that's not the right word, a range of precision, that's the word I'm looking for. So precision, how precise does this mean? So a really wide confidence interval, I don't have a lot of faith in, but a smaller confidence interval I have a little bit more faith in. So I would believe that their scores for this group of students would be about 1310 to about 1430 is what I should expect people to score in this sample. I don't know that that tells me a whole lot about the population because this is just one sample, but it gives me an idea about what I might expect from the population. Okay. All right, the other thing we're going to be interested in really is effect size. So we talked about Cohen's d in the lecture video, but I would also like to calculate that effect. So we just click on effect size and it pops up right here. And so Cohen's d and the t statistic are intrinsically linked. The t statistic tells me that I have a 4-to-1 ratio of good variance to bad variance, which means that, about 4-to-1, I'm going to get the effect that we did. But p doesn't just tell me a whole lot. Like, the p-value is specific to this sample and this sample size and this difference, but Cohen's d tells me a lot. And so what that tells me is that it's a large effect. So I got a 4-to-1 ratio, but a standardized effect is that it's fairly large. And I like having effect size because p-values to me are kind of useless. They tell me the probability of getting this effect if the null was true. And remember in the last video we talked a lot about like what does it mean for the null to be true, to really expect that. But a effect size gives me an idea of how big is the difference between groups, and then what might I expect the next time I took a sample from this particular school, and how might I plan in the future for studies on this type of thing. So we're going to talk a lot about g-power and how to calculate sample sizes from known effect sizes. So this is the main thing that you're going to want to do for a t-test. We'll talk more about normality and assumption checks in the data screening video, but this is what you would want to be able to report. Now you could leave it here in this table, so this is a very nicely formatted APA style table for both of these, but I would say that one row of data is usually not presented in a table in this format. So instead what you might do is present it in this style. So list the mean, the standard deviation, and then this again is APA style. So t, here's degrees of freedom. I put in my t-value right here. I did 0.001 for p, because it's not less than 0.001, it is 0.001. And then I listed my Cohen's d value. Okay. So I could write all of this in one sentence instead of having two kind of separate tables here. Okay, so that's single sample t. Let us try now something else. Let's look at a dependent t. So a dependent t-test is when you have one group tested twice. So this is very popular for before and after designs. Let's say you want to give someone an intervention, so you tested them first, you gave them the intervention, you test them again to see if their scores are changing. So very popular in clinical designs because I know that whatever I did to them changed their scores in the middle. So in this example from an intro psych textbook, what I have is I gave 7 people a test of belief in the supernatural. I made them watch a silly science fiction movie, and then I tested them again. So what do we expect to have happen to their scores after showing them this movie? So let's open that data set. So File, Open, Computer, Browse. This dependent T data set. And so I have that set up. Here we go. Is before and after, so we want each person gets their own line, and that is going to be true for any type of repeated measures data where people are tested repeatedly or tested on multiple items. Make sure each person has their own line. So this is participant 1 all the way across. So I've got before and after. I'm going to click t-tests, paired samples t-test, and it's the same thing as dependent t. Now you can do this in any order that you want, so I can put after first or before first. And that will only change the sign of the test statistic. So I moved it over, and you'll see how I got this little line bar here thing. because it has to be set up in pairs. So you have to have at least 2 for this to work. So automatically get my t-test here. I did before minus after, and I got a positive value of t. So what the hell does that mean? It's a small ratio, and it's not significant in our normal 0.05 criterion. Hey, I didn't want you to go away. There we go. So we're going to take this one off since I accidentally did it twice here. So let's add some descriptives here to see what this number actually means to us. The before mean was 5.5, and the after mean is 4.4. So clearly their scores are going down. And so it's always helpful to have this sort of the scores for each one, because then I can tell what's happening before to after. So the scores are decreasing. But the way I subtracted them, that's a positive number. You could ask for the mean difference. Sometimes people report the mean difference and the standard error of the differences. That's also popular. But given I don't know which way they subtracted, I like seeing the individual numbers, because then I can judge for myself what this 1.1 change means. It means those scores are going down, even though it's not negative. So I'm going to turn that off. I definitely want an effect size, so I get my Cohen's d value here. Now, a word of warning, if you look at the report I have right here, I have d average. What JASP gives you is d differences. So I would tell you to write that up as d diff, or d differences. There's no standardized way to report this. This is just the way I've been doing it. And we would say that's 0.54, but not in subscript here. Turn that off. Okay. And so what is the difference between d diff and d average? Well, d differences is the ratio of the mean difference over the standard deviation of the differences. Almost said the wrong thing. It's mean difference over standard deviation of the differences, which you don't get in this output here. T is the mean difference over standard error. So 1.143 over 0.8 here is this number. That is a really popular way to calculate Cohen's d. So I'm going to turn this off so it's not confusing. Is to calculate mean difference over standard deviation of the different scores. However, some people think that that is a little biased, too big, which is always a bad thing. We don't want to overestimate our effects. And so you'll also see people report d average. The average is the mean difference score, so mean minus mean here, so 1.1, divided by the average standard deviation on the bottom, instead of the standard deviation of the differences. That sounds like semantics, but mathematically they're pretty different. And so you'll see people report it, either one, but the real problem is that people don't tell you which one they're doing, so you don't know how to judge what the number is that you're getting. And so if you're using JASP, you should report it as d differences, because that's the one they're calculating. Okay. All right, so that's all we need from here. We could also look at a confidence interval, but it's going to be the confidence interval of the mean difference score and not the confidence interval of each individual mean. But I can tell that that confidence interval crosses 0, which is why it's not significant. So remember, P only tells me about this sample if the null is true, so I'm really more interested in the ratio. So 1.4 to 1, which to me sounds pretty much like it's pretty equal, and the effect size. Now this is a medium-sized effect, and so I'm not sure what to believe here, because T here tells me that it's not really a big ratio of good variance to bad variance, but Cohen's d is kind of in the medium range. So really what I would tell you is you would need to rerun this study with more people. 7 people, so degrees of freedom, 7 minus 1, is not really enough to judge this effect. So it could be that I got 7 weird people, and that is what's driving the effect size being medium. Or it could be that the effect size is really medium, but we just don't have enough power or enough people really to find that effect to be significant. So kind of a tricky one here. I'm not saying that there's no effect, but I'm saying right now we don't have enough evidence to support saying that this is going to be an important effect. Because 7 people is always hard to believe, so you need a lot more people. All right, so this is how one way you might report a dependent t-test before and after our t-values here. So we could always use this table here of the descriptives and then just report these in text, or you could do both. Okay. So that's dependent T. Now let's try independent T. So independent T is where we have two totally different groups of people. And in this example, we have people that are hypnotized, and then when we measured their accuracy of remembering a mock robbery. And then we also did a control group who wasn't hypnotized. So as a kind of a classic experiment where one group gets the experimental manipulation and one group doesn't. So let's open up that data. So File, Computer, Browse, and then Independent T. Give it a second to open. There we go. So one issue I have here with this data set is that I don't have the groups labeled. Now, I know the first group is the hypnosis group, and the second group is the experimental group. And as you'll see in one of the next videos, the only real way to get labels on here that'll help you out is to open up the Excel file and edit it to have those labels. So that would really be the first thing I'd want to do. But in this particular case, let's just try the Ttest without doing that, because we're going to cover data screening, editing those things a little more in one of the next videos. Okay. So let's click Ttest. This time it's independent samples Ttest. We're going to take our group variable, anything with the labels or the groups here in the grouping variable. And notice that it has to be a little, the nominal or the interval type scale here. Is to correct questions in my dependent variable. So it really should be a scale variable, and I could go in here and change that because it really is a number here. I'm going to delete this one, click remove to make the extra one go away. So that automatically gave me my T here, and it says that the ratio is negative 2 2/3 to 1, and that is significant, just barely. So I'm going to be really interested here in my effect size, because 3 to 1 ratio is it's okay, but let's see what that effect, how big that effect is. So I click effect size to go ahead and get it. It's 1.88, which is a really large effect size. So not only is it significant, less than 0.05, it's also a big effect. So this is going to be a fairly believable thing, except that I only have 8 people in the study. Now degrees of freedom here is not n-1. Everything we've been doing has been n-1. Let me click descriptives here. And so I've got my two groups. So better if I had labels, right? And I have 4 and 4. So if it was n-1, it would be 7. But in this case, because the groups are separate people, two totally different groups of people, it's n-1 plus n-1. So it's 4 minus 1 plus 4 minus 1. And that's where the 6 comes from. Because we've got to calculate the mean for each group. So I can keep 3 scores the same for each group, but I got to have that one last score to be able to keep these means. I'm sorry, I can vary 3 of the scores. So this is where a table would be really nice, except with labels of those means. And let's see here. Group 1 was the hypnosis group. Group 2 was the not hypnosis group. So our t value is negative because we did 17 minus 23. And it looks to me like not hypnosing them, good grief, not hypnotizing your participants actually worked better. So it's kind of, if your expectation was that under hypnosis they should remember better, you're actually kind of totally wrong. We could add the confidence interval here, but again, it's going to be the confidence interval of the mean difference, which if I click here, I would get, so that mean difference is 5 points difference between each group, and that confidence interval is the mean difference for that. So that's not as popular to present. It's more popular to present the means of standard errors for each group. And then we'll talk more about plots. You can click to add a plot, but I would argue these plots, while cute, since they're not editable, are not super useful at the moment because I can't edit them to be a bar graph, because this more appropriately should be a bar graph. And we're going to cover graphs next, and we'll talk about that some more. So I'm going to turn off my plot here. We can do some assumption checks, so we could do normality and homogeneity, which is equality of variances. We're going to cover that more in our data screening video. So there are other options that we could click on here. but I'm just kind of covering very basic, simple t-test. Okay, so that's independent t. Here's how I might report independent t, report each group, the degrees of freedom here. Oh, I forgot to say, if you're reporting things in AMA style, that tends to be a sub, like, let's do this. I'll just copy it. Tends to be more like this, depending on the journal. I've seen it kind of both ways. But you still need to report the degrees of freedom, that it's a t-test. Here's my t-value. P, I rounded up to 0.04 just to do 2 decimals. You could do 3 decimals. And our effect size here. Last but not least, let's do a very simple correlation. So we've measured femininity and sympathy, and we're just going to see if there's a correlation between those two variables. Let's go back to JASP here, click File, Computer, Browse, and I'm going to click on my correlation data set. Okay, so I've got my femininity and my sympathy, so this is a big data set, so I have a lot more participants to measure. Under regression, we're going to click correlation matrix. I'm going to move both of them over. I could do a whole bunch of variables, but I'm just going to use these two at the moment. Pearson is your traditional R value. There are some non-parametric versions called Spearman and Kindles, but we're just going to stick with Pearson. Report significance means it's going to show you the p-values, otherwise it's not going to show you the p-values, but we like to know what they are. You could add little stars. This is the more traditional. If you did this, this would be more like what SPSS looks like. I would like to see p here. You can actually get the confidence interval as well. And so that's really handy because confidence intervals on correlations are kind of a pain in the ass. So it's really nice that it shows you the confidence interval for it. Yeah, turn that off right now. So what does that tell me? And what it shows me is that feminine here and sympathy are correlated at 0.18, and that is less than 0.001, which is really useful. The nice thing is that it doesn't show it to you twice. So feminine and sympathy, that's the same correlation here, so it just left it blank. The dashes here are where it would be correlated with itself, so it just kind of ignores that point because it's going to be 1, hopefully. If you've done, unless the math has gone completely haywire, the correlation with itself would be 1. And so that's how you would run a correlation. The easiest way to report that is like this. Correlation, remember, is its own effect size, so I don't have a separate effect size for that. And this would be somewhere between a small and medium correlation because 0.1 is small, 0.3 is medium. All right, so all that together is t-tests and correlations in JASP, which means that you're now able to go do the basics homework.